Okay, good morning. So today we continue to talk about the chapter 2, that is the electromagnetic circuits. So before we come into the the contents about these chapters, let's have some fundamental knowledges would like to transfer to you before, right? Let me write down some things here first, because some students may not very familiar with the electricities. Now, first, sentence I would like to write here. Electric charge produce electric field. Okay. Field or electric force, right? Electric field. That point from positive charge to negative charge. Okay. So we say electric field charge Q produce electric field E, generally, E, which is that point from positive charge to negative charge, right? So that is the Q, produce electric field. Okay. So E field drives electric charge moving, to move, So electric field, right? E field, to drives, electric charge to move. So that is the current. Along the E field. That is the current. Okay. Current I produces magnetic field B. Surrounding the current line. Okay. That is the electric field cross the magnetic field. Okay. They are perpendicular to each other. Okay. So integration of E field along its line for certain distance, that is the voltage, or electromotive force. Hear me now? Any sound? Okay. So, okay, thank you. So if any problem, please let me know immediately. Okay, thank you. Okay, so now let me repeat these issues. So as I wrote here, okay, you can read of it. So electric charges produce visible electric charge, right? Electric charge we can see it using the microscope. So electric charge produce an electric field that point from the positive charge to negative charge. So electric field is a vector. Okay, it has amplitude and has directions. So in short, that a charge Q produce electric field. Okay, so that's the truths, right? That be discovered by the human beings. So electric fields, we usually say in short, E field drives electric charge to move along the E field line. So because E field has directions along E field line, that is the currents. So moving charge form the currents. Okay, now another truth is, this is the first truth. Another truth is that current, that is moving charge, the current produces magnetic field surrounding the current line. Okay, so you can imagine, right? If you have a current on a line surrounding the current line. Okay, then this means that what? This means the electric field and the magnetic field perpendicular to each other. So the cross here means that these two always cross each other. Always cross each other. Electric field, magnetic field, electric field, magnetic field. Okay, so that's the basic issues you should remember. Okay, once somebody asks you about electric field and magnetic field, current and charge, you can teach them this point. Okay, integrations of the E field along its line for certain distance. Okay, that is the voltage or electromotive force. So now you understand, okay, what does it mean by the voltage? Okay, voltage is volts, right? Electric field is volts per meter. Okay, volts per meters. Okay. Now, this is how the electric field and magnetic field be produced. All comes from the charge moving or not moving. Okay, so charge is the origins. Charge is the electric circuit origins. Okay, magnetic field B1 and another magnetic field B2 intact. That is the magnetic force. Okay, so combine all this knowledge together, it is not difficult for you to understanding the following two principles. Okay, remember this one. Okay, so this is the universal laws. Okay, no theories behind it, but the truth. Okay, so remember this one. Reverse what I write here. So that's very important. Probably will be tested or examined. Ask you to write some things about these issues. You can read more reference books to get some more details on it. But remember, no more theories behind it. It is just the truth in the universe. Okay, now go ahead to see two basic principles in practice. Okay, so now let's looking at two very important principles. The first statement is that a conductor carrying current into a magnetic field experiences of a force. So now you can understand of this one. A conductor carrying current, that means the current, there is a current, right? The current produces magnetic field. Okay, current produce magnetic field. Okay, this current produce magnetic field. So, sorry. We say this is magnetic field 1. Okay. This is magnetic field B2, right? Okay. So a conductor carrying currents which produce magnetic field B1 into a magnetic field which is the B2 experience force. Okay. That's what I just wrote, right? So two magnetic field intact produce force. So this force, okay, this force push the conductors move because the conductor carrying charge. Okay. Okay. So conductor, what does it mean by conductor? The conductor means that there are free charges. Free charges. So a conductor with free charge carrying current produce magnetic field B1 into magnetic field that is B2 experience of force, mechanical force. Okay. So because conductors making the charge cannot escape from it. So the charge try to move, but it cannot escape from conductors, therefore making the conductors moves. Okay, that's the principles of electric motors. Okay, hope you understand the principles here. Okay, so the second point is that a conductor moves through a magnetic field, produce a electromotive force on its right. Okay, so this is principles generators. Now, once again, a conductor, with charge, moves, moves, moves. When conductor moves, what happened? Invisible, right? Invisible currents, through a magnetic field. Induce, right? Induce an electromotive force that making the charges move, right? Making the charges move in another way. Okay. Electromotive force. Okay. So electromotive force be formed because that the conductor moves inside the magnetic field, making the charge separate, Okay, one positive charge at the one end of the conductor, the negative charge at another end of conductors. So this separation form a strong electric field that further to push the electrons outside the conductors to the users. That's the principles of generators. Anyway, so these two principles is just the applications of what I just talked a few minutes ago. Now, let's focus on the magnetic field issues. Okay, we move on. Next slide. Okay, so therefore, we have to touch about the electromagnetic field issues together, because once there is a charge, there will be an electric field. Once there is an electric field, the charge will move. As the charge moves, there will be a current. Once there is a current, there will be a magnetic field. If there are more than one magnetic field or more than one currents, then they will have right interactions between the magnetic field, or interactions between the charge, or interaction between the currents. Anyway, the same things. So they will have force. Okay, this force acts on a charge, but the charge constrains inside the conductors. So the force become a mechanical force, right? Another way, if you have the electric field inside the conductors, the electric field will push the charge inside the conductor separate to the end of the conductors, because the conductors constrain the charge inside the conductors, so making the conductor has voltage difference at the two ends. So that's why we have the electromagnetic circuit always be twisted together. So now, so for these chapters, first of all, we have inductions, as I just said to you. Then we will talk about the magnetic field. So we'll talk about the magnetic field force. We'll talk about the induced electromotive force, as I just explained to you. Okay, so once there's a current, the current produces magnetic field. How many magnetic field produced? Okay, so how to produce strong magnetic field? How to produce strong magnetic field with current. Okay. So the inductive circuit means that how to produce strong magnetic field with current. So once there is current, that produce strong magnetic field. In previous circuit, DC circuit, we fix on how big the current produce. So we can make in electric circuit how to electromotive force. Okay, so the electric circuit, we fix on how to produce strong current with electromotive force. Okay, so we're given a voltage that we produce, right? We discuss about the current issues. But, as I just said, when there is current, there is a magnetic field. So, therefore, in some circuit, so the current very strong, and also the current distributed in a way that the magnetic field also be very strong. So the magnetic field, when the magnetic field produced by the current make issues, this circuit becomes inductive circuit. So inductive here is inductions. Is inductions. When there is additional magnetic field, when the magnetic field changing, then they will have induced electromotive force on it. Okay, so that's the inductive circuit. Here, so with a method to produce so inductive circuit discussion how to produce strong magnetic field with the current go through the conductors. Now, so in practice, we can use in the coilers, coilers, as I show here. So we have air-cooled coilers, air-cooled coilers that to produce strong magnetic field, to produce strong magnetic field. Okay, now once we talk about produce strong magnetic field, so now how much strong magnetic field, how strong magnetic field is. Okay, what's the inductions? So we have the magnetic circuit, we have the magnetic parameters to describe the relationship between the current. Okay, relations between current, magnetic field, and a electromotive force and conductors. Okay, the conductors. So conductor, the conductor has length, right? Cross area, turn, numbers, and so on. No sound? How about sound now? Oh, yes, right? Okay. Okay. So it's good, right? So then, then we should discuss about the relationship between the currents, between the magnetic field, between the electromotive force, and between the conductors used to produce magnetic field. So when we talk about conductors, we have the length of conductors, cross-section area, conductors, turn numbers, conductors, etc. So therefore, we have the motors to analyze the parameters. Okay, so therefore, analytic motors, to describe the relationship between them. So by using these motors, we can find out so based on the motors, we will find that in addition, besides resistance, there is one more parameter L, that is the inductance that describe the capability of a conductor to produce B. Okay, so after analysis, we introduce, besides the resistance, we introduce one more parameters. These parameters, okay, inductance. Okay, we using the symbols L represented. Now, what does it mean here? Very important. Okay, the inductance used to describe the capabilities of a conductor to produce magnetic field B per ampere. Okay, given 1 amperes on the conductors, how strong the magnetic field is. That's the inductance. Okay, that's the inductance. So similarly, now, what's the resistance? The resistance is, okay, the users is the load to consume voltage, the capabilities consume voltage, okay, to produce or consume voltage with 1 amperes, right? So 1 amperes, okay, so 1 volts, that 1 ohms, right? So 1 ampere times, okay, the resistance, okay, is the voltage that get cross the load, right? So reluctance, okay, is the capability of a conductor, okay, to consume voltage, okay, with 1 ampere. The inductance is the capability of a conductor to produce the magnetic field per ampere, okay, per ampere, with 1 amperes with it. Okay, so that's the right subtitles I listed here, okay, because okay, then okay, in the slides follow this, we will write one by one talk up these concepts. Okay. Now, okay, so electric, right? In combinations, electric system can be represented by a equivalent circuit based on the design data or testings. It including, okay, so the current voltage. Besides the current voltage, we have 2 more, okay, parameters. The parameters, as I just introduced to you, we have the resistance, we have the inductance. Okay, so far you learned about resistance, and today, okay, talk to you about another one, inductance. Okay, so the currents in conductors establish the magnetic fields. These fields are used, okay, as I just said, these fields are useless or okay, useful. So the useless in case of cables and electric installations, it causes voltage drops or electromagnetic interference, as I just explained to you. Useless one, because magnetic field okay, interacts with the another magnetic field. That means magnetic field interacts with the currents, So they block the current change. So blocking the current that is produced voltage drops. Okay. Okay. So useful that because when you apply a current to a conductors, then the conductors produce magnetic field. If you're using another magnetic field to interact with these conductors, then this conductors moves. So okay, this is useful case. Okay, if the conductors not move, you will making the conductors right. Okay, voltage drops. If the conductor moves, then okay, that is the machines. So use this or useful depends on the functions. Okay. Generally, in electric circuit, electric systems, there are currents there are magnetic field, there are charges, all are energies. Energies can, moves, from one side to another side. So energies must flow from electric circuits into magnetic circuits. When the currents and fields strength increase, increase, and vice versa. That means, as I just said, in the electric circuit, you may have the current producers, you may have the magnetic field producers. But the magnetic field produced by the current actually on specially designed conductors. So when the currents and magnetic field increases, that means there are energies from the electric charge to the magnetic circuit, from batteries to magnetic coils. If the current becomes smaller and the field become weaker, that means the energies released by the magnetic circuit and back to the electric circuit. There is a parameter inductance that links the electric and magnetic circuits. Because the inductance, as I just said, describe the capability of a conductor produce magnetic field with 1 amperes. So if you have 1 amperes, the amperes times this inductance, that represents the magnetic field, magnetic field. Vice versa, if you have a magnetic field, that describe, that divided by this magnetic field, inductance, that is the currents. And this is linkage parameters between the electric and magnetic circuit. Now, thinking about this one, this will help you to understand the natures of the electric field and magnetic field. So here we talked about how to produce magnetic field with a small current, but produce strong magnetic fields. So we talked about concepts of magnetic fields. A coilus, suppose this is conductor, we can make it as a coilus with current. So the current will produce magnetic field Suppose this is a conductor. We making the conductors to wood, like this. This is the coilus. This is coilus. If you have a current in this direction, as I just said, you will have magnetic field surrounding the current lines. Here, the same surrounding the current lines. So a coil would, in the same direction, produce a concentrated magnetic field inside the coilus. When a current flows in it, because the magnetic field perpendicular to the currents. If you have a coilus, horizontally, like this, then you have a magnetic field inside like this. So if you have a current on the coilus, this coil current directions like this, the magnetic field will perpendicular here. So that's why we said a coil would, in the same direction, produce a concentrated magnetic field when air current flows on it. Okay. A DC current generates a magnetic field in a coilus of fixed polarity. Fixed polarities. We define the magnetic field, okay, that from North Pole to South Pole. North Pole to South Pole. Okay. Externally, so start from the North Pole, then to the South Pole. That's the polarities. That's the polarities. So this is like a magnet. Okay, so DC currents generates a magnetic field in a coil with a fixed polarity, no change. Now, if we have an AC current generates a magnetic field in a coilus of alternating polarities. We not yet learned about AC, but here, okay, you should know that the AC means that the current polarities changing with times. As a result, the magnetic field produced by the current, AC current, also changing their polarities. Okay, North Pole, South Pole, North Pole, South Pole, they're changing. Okay, so now, what's the directions of the magnetic field? We just said that, okay, so the current produced magnetic field. Look at it here, okay, right hand screw rules, right hand screw rules. This is the directions of the current on the coilers. The thumb, right, okay, point to the directions of the magnetic field inside the coil. This is a coil, coilers, C-O-I-L, coilers. So the current, the four figures points to the coil, right? Current there. This is directions of magnetic field. It points to the North Pole. North Pole. Okay. So here, right, is just for one straight line. For one straight line. Okay, one straight line. Okay. Right. That is right-hand screw rules. Coilers, directions of the currents, direction of currents. Direction. If the currents, right, okay, reversed, the magnetic field will reverse. Okay, magnetic field. So the magnetic field is vector. Is vector. Okay. So this is the right diagram showing you what form a current flow produces a magnetic field that maintains a fixed polarity. That's the DC. So basically speaking, what you have here, so you have a magnetic field produced like this. Okay, produced like this. Look at it here. So produced like this. And similarly, if you have a coil like this, like this, like this, have your current in this direction and current here in these directions. You have current here, these directions, these directions, these directions. Okay, in this direction. This is the current directions. Okay, then the magnetic field, okay, thumb point to the North Pole. But remember, you can reverse the current, right? You even can reverse, right, the reading directions. Reading directions. So with the same currents, okay, you can change the, okay, okay. So the magnetic field will be look at here. So this is the coils that would in this direction, with the current in this direction, produce the magnetic field inside the coil in this direction because this principles. Okay, now for the same currents with the same coils, if you change the coils directions, okay, you can win the current in different way, right? Win current different way. Okay, so if the coil's direction change, then even the current, right, in the second node change, magnetic field reversed. Okay, so that's the points. That's the points. Okay. Okay. Now we just talk about the how to produce magnetic field and the magnetic field directions. Okay. Right hand screw rules. Right screw rules. Now we're talking about the force, magnetic force. Magnetic force converted into mechanical force because we usually using the conductors carrying currents to produce magnetic field. Two conductors carrying currents interacts produce force, making the conductor of smooth, right? Now we're looking at the directions of the force. So F here is the force on the conductors in newtons, okay, not kilogram, right? Okay, newtons. Force is newtons. I represent the current. So if we have current, okay, several amperes on a conductors with a length L, then emitters, then a conductors, and the right angles to magnetic field may produce suffer a force. So the force proportional to the flux density, magnetic flux density, the strength, okay, the magnetic field strength. B here is the flux density or magnetic field strength, okay. But magnetic field, many lines, okay, so this represents how many lines per square meters strength, okay. So cross the currents, cross the directions of the conductors. A dot products, cross products. Dot products, right? So means that two convectors for examples, this is E field that has directions. This means dot products. Another one, say the current has directions, or the B field has directions. That will be the values of the E, the values of the B at the cosine, the angles between them. So dot product means that for two vectors, one vector for is the E has directions. The other one is the B has directions. So the two dot products means that the values times their cosine, okay, cosine angles between them, okay. This is dot products. Cross products. cross okay. So suppose we have two vectors which has magnitude, which has directions. We have two magnetic E, okay, and B, two vectors, no matter what it is. And between them, they have the angles in directions. For dot products means that the products, E times B, that values and cosine theta between them. What does it mean? This means that if the E in the same directions with the B, then it has the maximum products. If they are perpendicular to each other, they will be 0. Okay, because cosine 0 be 1, cosine 90 degrees be 0. Now, cross product, the E and the B, the magnitude products, okay, and the sine theta. So if the theta be 0 degree, sine 0. If the theta be 90 degrees, sine be 1. That is the cross. That means if the E and the B cross to each other, then the force be maximum, right? This is example here, the E and the B is not what, is two vectors. That means of it. Okay, now looking at here, so the force proportional to, right, flux density B times the current I. Okay, the current usually on the conductors. So if the current cross, okay, the magnetic field, okay, then the force will be, okay, the products of the B, the length, and current I. The longer of conductor, the bigger the force, right? This is, okay, easy to understand. So the B is the flux density, which is the magnetic field lines per square meters. Okay, flux density. Okay, this is the flux. Okay, flux magnetic field lines. Electromagnetic field lines, right? Okay. Okay. So for your good understanding, okay, we're using the right layman language to telling you what does mean. So the magnetic flux density, we say the magnetic field density, which has a general unit, Teslas, okay, Teslas. But, okay, it actual meaning is that magnetic field lines. So we have magnetic field lines per unit areas. Okay, this is per unit areas. How many magnetic field lines per unit areas? The flux, the waves, what does mean is the total magnetic field lines within certain areas. If you have, right, a coils that have, right, cross-section area of A, cross-section area. So the total flux lines, okay, over the sectional areas A, that is the flux density B, would use it to, okay, describe the strength of the magnetic field. Okay. Okay, so suppose that you have a strength magnetic field in this direction, strength B in this direction. You have a current in this direction or conductor in these directions. Between them, they have an angle theta. Then, okay, so the force, okay, the inner page, okay, so using the left hand, okay, using the left hand, right? So screw from the B field to the I, because this is B, from B to I, using the left hand from B to I, from B to I. Okay. Okay. From B screw to I, then the thumb point to the force directions. So the force also is a vector. So is a vector. That's the meaning here. Left hand rule. Okay. So the first figure, for example, you point to the magnetic field. The second figure, you point to the right currents. The thumb point to the force, mechanical force. Anyway, mechanical force. Left hand rule. Okay, so this is the magnetic field. This is the current. First, right, figure B field. Second figure, current. The thumb, mechanical force. Can you see my hand? Right, mechanical force. That's it. So now we have learned about the how to produce magnetic field. Okay, what's the magnetic field? How to produce force using the conductors carrying current in a magnetic field. So we can using a conductors carrying current moving magnetic field that produce magnetic field. That is the force. It is this force that drive the conductors moves to produce right rotations. Okay. Anything else? We also said that we can use in the magnetic field move the conductors in magnetic field that produce electromotive force. So we have talking about electromotive force. Electromotive force. Anyway, what happened to it? There is no. Anyway, so electromotive force determinations, Lenz's law. So as a matter of fact, at the beginning, we already talked about that, okay? When you're moving conductors in a magnetic field, that produce electromotive force on the conductors. Vice versa, if you keep the conductors not change, but you change the magnetic field. Anyway, okay, electromagnetic field inductions, Faraday, this guy, discovered that a current or a magnetic field could be produced by movements of magnetic flux relative to a coils. Okay, relative to coils. So movements of magnetic field flux relative to a coils. Relative to a coils. So now, suppose we have a coils, a coil that has 10 turns with flux density D at a cross section area A. Numbers N with a flux density B. and a cross-section area A. So then the total flux touch the coils is the total flux. Okay, that's the first is the B times the A. That's the phi. Okay, the times the n numbers. Okay, this is the total flux touch the coils. So the next note says movement of the magnetic flux relative to coils. So movements relative to the coils means that okay, if there are a total flux linkage changing with times, then there is a magnetic field, okay, electromotive force be generated on the conductors. That's this one. Relative moments includes the move of conductor and the change of the B field. Change change of the total okay. Further explanation on this one. So that means okay, relative movements including the move of the conductors and the change of the magnetic field, right? So if the conductors not move, okay, and the magnetic field changing, that's okay. In any way, the change of the total flux linkage, change of total flux linkage, okay, that is the okay, big phi. So if this changing with times, then you have a magnetic field, right? And you have an electromotive force generated here. So this changing, okay, look at it here, this changing, it may be the changing of the B, maybe the changing of the N, moving of the N, okay, moving of the N, maybe the changing of the cross-section area. Cross-section area can be changed, right, of the coils against, right, against the magnetic field, okay, in the magnetic field. Because you can change the directions of the coils when the magnetic field, right, magnetic field changes. Okay, so that's the meaning of it. In most of the case, okay, in the electric circuit, we fixed the conductors or coils positions. Okay. we may fix the coilers. Fix the coilers. And change the B field or rotate coiler in constant B field. Okay, so in practice we may have two cases. So we may fix the coilers and change the B field, particularly in the AC circuit, right? So with the coilers fixed there, but the current changing. Okay, so this changing, okay, create the electromotive force. So this electromotive force is, we can see it as a voltage drop, right? Okay, so or we rotate the coilers in a constant B field. This and this. Okay, what's this? We fix the coilers and change the B field. What's this? Okay, so inductor. Okay, so the coilers and change, right, the B field. This usually we have the inductors on the circuit that using the changing current, because when the current changing, the B field changing, there is voltage induced on it. So this is the inductors in the circuit to control the currents changings. Okay, so the rotated coilers in a constant field. Usually in generators we use these principles. So this is, okay, the induction issues. The voltage A and total flux linkage produced by a given coilers. Okay, Okay, so the negative sign here stands for opposition to the change. That means if the E field increase, strengthen. Okay, if the magnetic field, okay, if the flux increases, right? Okay, increases, then you produce a magnetic field, right, making the flux decreases. Okay, in other words, that, okay, so the direction of induced electromotive force is always such that tends to C-type a current, or opposing the motions or the change of flux responsible for inducing the electromotive force. Okay, so in other words, if you have a electromotive force or a current to produce magnetic field, this magnetic field generate electromotive force. Then the generated electromotive force try to C-type additional current that to weaken against the change of the current. So for example, original current that is increasing, which generate additional electromotive force that produce a current, tends to produce current, to reduce the currents. That's the meaning of it. If the original current is decreasing, therefore induce electromotive force. The induced electromotive force tends to produce additional current that increase the currents. Okay. In other words, that the additional current try to increase magnetic field, which induced electromotive force try to produce a current that try to decrease the magnetic field. Okay. Anyway, induction against the change of the original one. Okay, so in one word, induction against the current or magnetic field change. Current or magnetic field change. Okay, so if you have no change, nothing to do. If you have no change, nothing to do. If you try to increase, I try to block you increase. If you try to decrease, I try to block your decreasing. So making the current, right, and the voltage has, right, some different changing speed, different changing phase. That's the phase. Okay, that's the phase. Okay. Far slow. Now we come into a complete electric magnetic circuit as we show here. Suppose we have a electromotive source here. We have an electromotive source that have a voltage changing with times. Here we're using the VT represented, changing with times. On the circuit, we have a resistor R. We also has a coilers. This is a coilers. As we know that once there is a current, this currents produce magnetic field. Okay. So the magnetic field has magnetic field strength, okay, proportional to the current, and also proportional numbers here. So the cross-section area of the coilers here, the turn numbers of the coilers here, each part of the turn numbers experience the change of magnetic field. So the total flux linkage on the conductors touched with conductors, right? More turn numbers, more magnetic field touch with the conductors. Okay, one turn, just one turn touch, one conductor touch it, right? Turn, then more conductor touch it. So this turn numbers of it. We call it, this is the total flux linkage. So the total flux linkage, okay, that link to the coilers is phi here. And previous slide showing you, okay, when this flux changing with times, there is a voltage generated here. This voltage against this voltage, always. This voltage against this voltage. Okay. So the current here generated against this voltage. So as a result, the source voltage has to overcome the voltage drop on the resistor R and voltage drop cross the coilers. Okay, that's it. So the source voltage and the resistive voltage drops and the inductive voltage drops. Someone said, why you say drops? Because I said that it is against this one. If this increase, this decrease. Okay, right? If this decrease, this increase. That's it. Okay, the changing rate. So we have a new, right, formulas, look at here. Originally, in comparison with the Ohm's law in DC, okay, now that's the DC. In the DC circuit, the current no change, right? So the d phi dt be 0. So there are no inductions. So we have the voltage, because the voltage not change, okay, current not change, okay, resistance. Okay, for a given resistance, there will be this one. This is the DC circuit. Okay, this is the DC circuit case. Now, if the current changing or voltage changing, or there is movements of the coils in the circuit, then the Ohm's law be expanded too. This is new Ohm's law. Faraday's law, that is Ohm's law. Okay, that's the meaning of it. Generally, we suppose the coil no change with times, and we can assume that the magnetic field changing with the current. Then because the B field is proportional to the current, okay, times we say coefficient. Okay. B, sorry. Okay. The total flux can be simply right if the coils is fixed. Okay. The total flux can be simply right into a current times a coefficient, coil coefficient, L. Okay, that's because the current produce magnetic field. Current produce magnetic field, therefore produce flux. And for a given coils, it has certain turn numbers with certain materials with certain cross-sectional areas. Okay, so we can simply for a given coils introduce one coefficient L. That's the inductance. Okay. Okay. Now that's to see how to inside coils to produce magnetic field. How to describe the relationship between the magnetic field and the coil parameters. Yes, you are right. Later on, okay. So that's the purpose. As I just said that, we can introduce a so-called inductance to link the current to the flux, therefore link the current to the circuit, right? In the current to the circuit. Then how to find out the inductance? So here I wrote, right? To find the inductance L is the magnetic circuit analysis purpose. So what we are going to do is that by analysis the circuit to get the inductance, equivalent inductance of a given coils with current. To do this, that's to follow the same right principles we did for electric circuit. We define several parameters. The first parameters we get, I follow the magnetic circuit. We define a magnetic-motive force, which we supposed to drive the magnetos to move, right? So F here is the magnetic-motive force that like very similar to the electromotive force V. So which with the current and the turn numbers, okay, more turn numbers, stronger magnetic-motive force, just like a battery. So the current in the battery, okay, you have the charge, right? Charge. In the magnetic force, we based on the currents, okay? Turn numbers of the currents. More turn numbers, more currents, and more strong magnetic force, okay? And also a magnetic circuit reluctance. Reluctance, okay, is the, okay, similar to the resistance. That means to, okay, produce the flux. We have a coils. The coils magnetic force. We introduce, right, the reluctance. Reluctance is the path, okay, is the path, okay, a force that, okay, that to allow the magnetic field goes through it, okay, just like the resistance, that is the opposition force that to block the current go through the conductors. Reluctance is a kind of the magnetic, okay, opposition force that to block the flux go through a given area. Then, in a simplified analysis, the flux linkage is given by, okay, flux equal to the magnetic force over the reluctance. Okay, similar to the Ohm's law, right? Very similar. Okay, magnetic force, reluctance, flux. So the flux here very similar to the current in the electric circuit. So this is the magnetic circuit. So this is very similar to the currents. Okay, follows the currents rows. This is follows the voltage rows. This follows the resistance rows. Reluctance. Okay. Now let's looking at the reluctance. Reluctance, the longer of the coils, the bigger of the reluctance. It's easy to understand. The wider of the cross-section area of the coils. This is the coils. Okay, the longer of the coils, bigger of the reluctance. The wider of the coils, smaller of the reluctance. Right? Okay, this is another one. The third one, different from the conductors, magnetic field can exist in the space. Am I right? Magnetic field can flow in the air. Magnetic field can flow in the wood. Magnetic field can actually get in anywhere in the universe. But depends on the material's nature. The magnetic field, right, flux will be different. Okay. One parameters, we call it magnetic field permeabilities. very similar to the conductivities of the conductors. For each conductors, we have the resistance. Therefore, we have the conductivities. So conductivities represent the capabilities of the conductors to let the current go through. Permeabilities is a kind of the parameters to represent the capabilities of the materials let the magnetic field goes through. A bigger of the permeabilities, the bigger of the flux, therefore the smaller of the reluctance. Because the magnetic field can exist in the air, magnetic field can exist in the free space. Therefore, for the free space, for the air, we have one permeabilities. These permeabilities, we use the mu0 to represent it. The mu0 is a constant, which is the universe constant. Okay, so for each materials, there is a permeability. We using the mu to represent it. And this mu of a given material, say the wood, say the magnet, say the coppers, they can be relative to the air's permeabilities. So the air's permeability mu0 here is free space permeabilities A. So mu0 is a free space permeability. It is a universe constant. Okay, so this is reluctance. So we have three new concepts: magnetomotive force, reluctance, and flux. So magnetomotive force, similar to the voltage. Flux, similar to the current. And reluctance, similar to the resistance in electric circuit. You can use in all the rules applicable to the Ohm's law is applicable to these laws. This is the magnetic field Ohm's law. Magnetic field, right? Magnetic circuit Ohm's law, right? You can understand this one. So in parallel circuit, in series circuit, and so on, network. So we will based on these three concepts to analyze a magnetic circuit. Before the analysis of magnetic circuit, we have to learn to draw a magnetic circuit, which is very similar to electric circuit. Once again here, so take time to digest, right? Digest the concepts of magnetomotive force and flux density and flux and reluctance. Particularly for the reluctance, there is a special coefficient, that is the mu, permeabilities. Any materials has a permeability, larger or equal to 1 mu. Mu0 is the free space permeability. It is a universe constant. Any materials can described using relative permeabilities. Relative permeabilities. Mu r here is relative permeabilities. Okay, mu r times mu zero is the permeabilities of a given materials. Now, as you know, in free space, E field exists, right? Yes, you're right. The mu r depends on materials. Okay. So the permeability depends on the materials. Materials different, they're different. So what you use the magnet, right? When you was a child, right? So you use the magnet, right? Play with the magnet. Magnet has a permeabilities very big, very big. With small current they can produce, right? Okay, very strong magnetic field. Even with no current, they have a strong magnetic field. Okay, but the magnetic field, right, may be right decreases with times. Okay, so that is a magnet. Permeability is very big. The similar to the magnetic field, for the electric field, so in free space, we have the electric field, right? So we also has the permittivities. So magnetic field permeabilities, electric field permittivities exist in the free space. So this also represents capabilities allowed the electric field go through a given materials. So in the free space, we have the epsilon, mu, epsilon zero, epsilon zero, another universe constant. So you may know of this one. Okay. So the epsilon u zero and the permeabilities mu zero together is two basic, right, universe constant. It is these two constants determine the magnetic field propagation speed, the light of speed. So these two constants determine light of speed. So at least we are living in one universe which has two constants, epsilon zero and mu zeros. If these two constants changed, the universe we're living in changed. We do not know whether this two constant is true for the other universe. At least, right, for our galaxy, this is true. On our Earth, this is true. In the solar systems, this is true. But apart from this, right, I don't know. But this two universe. So to constant. Similarly, magnetic materials, electric materials has different epsilon. Okay, that's the conductor, that's the wood, that's the plastic, has different epsilon zero, different mu. In electricity, so when we're talking about electric field and magnetic field, we have two basic coefficients, epsilon and mu, permittivities, permeabilities. Okay, so if these two be zero, nothing, no electromagnetic field. Okay, no electromagnetic field. So that's basic issues. Okay, any materials has epsilon, has mu. To electric field, they're just looking at these two constant. They never concern about the size of the material, never concern about the mass of the material, never concern about the colors of the materials. Electromagnetic field look the materials, touch materials based on epsilon and mu. Okay, to human beings, we look the materials, the colors, the shape, the strength. We weight the materials, the densities, and so on. But for electromagnetic field, they measure or detect the materials with the epsilon, with the mu. Okay, with the epsilon, with the mu. Okay, if the mu is very big, epsilon is very big. Okay, the materials is transparent to the electromagnetic field, right? That's interesting things. Anyway, so all I talk about this one, try to compare with the magnetic field and energy field in terms of their parameters, so that you can, based on your knowledge about electric field, to understanding the magnetic field issues. Now, we get back to the Faraday's law with the concepts of the inductance. As I just in the previous slide, we have the Faraday's law written in this way in a given circuit. We can further introduce a coefficient L, that the flux linkage proportional to the Li. Definition. Okay, so this is the definition of the inductance. Inductance L represents the flux linkage produced per ampere by a given coils. Okay. Then look at here, we have the equations with the source voltage, the cross voltage drop cross the resistance, and the voltage created induced cross the coils. So L is the inductance of the circuit or inductance of coils. Now, so L flux. Then you can got, because okay, for a simple cases, look here. So the flux linkage equal to L times I, and flux linkage equal to the turn numbers times cross-section area A times the flux, in a coils. And the flux produced by the electromotive force, magnetomotive force F over S. the reluctance, and the reluctance is equal to the length L over the mu A, and the F equal to turn numbers N times the I. Okay? Therefore, we have this. What's the phi? Phi is the Ni, okay? Phi is Ni over the reluctance, right? Over the I, right? Look at here. So the L is the phi over currents, and the phi is the turn numbers N times the phi over the currents. And the phi, look at here, is F over S. The F is Ni. So you have Ni over S. That is the phi times the original N. So you have N square here. N square here. You have the current I over I. Okay, current I over I. Because you have R here. So they canceled. They just the S. So N square over S. This is the N square over S. Okay, N square over S. Right? Get the point? So this is for a given coilus, a simple coilus. Okay. This is just a full simple coil case. The formula here is for a simple coil case. In practice, the circuit may include several coils and connected in different way. Different way. Pay attention to this point. Okay. Okay, so today, we've stopped at this slide, and next week continue to talk about the circuit analysis of the magnetic circuit. So please, after lectures, take a time, try to make sure that you have good understanding about the magnetic circuit. Magnetic circuit. So there are several new concepts: Electromotive Force, A, Flux Linkage, Phi, Reluctance, S, Permeabilities of a given materials, and also there is new laws, that is the Faraday's laws, which is the linkage of the electric circuit and magnetic circuit. A typical one is the formulas given here: electric circuit, magnetic circuit, the source. So now you look at the L inductance being introduced, which related to the current change. If no current change, the L terms disappear. That's the DC. So therefore, in a circuit with resistor and inductance, both resistor and inductance will affect the current when the current is changing. Okay, that's the end of today's lectures. Stop the recordings. So then there we'll have okay, so after that there is a visit from the SAO staffs for the Hardy students. So we will invite the enemies from the SAO to present some things to you.